So today I'd like to talk about the dynamical effects of shadows in transition disks. And the motivation is that as we see in ARM observations, most of the substructures are gaps and rings, and they're concentric. And we also have a lot of observations right now from near-infrared scatter light. And we also see a lot of asymmetric gaps and rings. But on top of that, we have seen more asymmetric stuff, such as spirals and shadows. And the focus of my talk today would be on these shadows. A common explanation of this shadow is that there is some mutual inclination between your inner disk and outer disk, so that the inner disk casts a shadow onto the outer disk. And the cartoon picture is like this. And depending on their mutual inclination, you can have broad shadow, which is caused by just slight misalignment between the inner and outer disk, casting a wide shadow 180 degrees. And you can also have a narrow shadow, which is caused by almost perpendicular inner disk. Then these two narrow shadows are separated by 180 degrees. And there are many previous works on interpreting the inner disk geometry, the mutual inclination, and even precession rate using the shadow. But only a few studies focus on, given that we have the shadow, what the dynamical effects would be on the outer disk. So that's my focus today. And it's the right time to do this project because we have the tool to do this. I use Radiation-Hydrodynamics code, namely Athena++, and this radiation module. This code can calculate the temperature in the disk self-consistently along with the hydrodynamics, and it can study both optically thin and thick regimes properly, and more importantly, it can treat the shadow and beam crossing problems. So let's take a look first at this narrow shadows situation, which is due to a polar disk in the inner disk casting two narrow shadows. I set up the simulation quite simple. I have a transition disk. There is nothing inside. And the inner disk, real inner disk, is not inside the simulation domain. The inner disk just provides attenuation of the stellar irradiation. This panel shows the midplane temperature. And as I turn on the shadow, turn on the inner disk, you can see that there are two shadows at these locations so that the temperature are lower. And immediately you see there are spirals, two spirals coming in from the outer disk. And that leads to very strong accretion. Later on, the outer disk you have vortex forming at the outer disk due to the Rossby wave instability, and eventually the outer disk also have spirals. So this figure shows that the shadow can lead to a strong accretion. In the beginning, I only have this simple sort of Gaussian-like profile. You have a ring here, and after 0.1 million years, you are at here, you gain a lot of material in the inner disk. And we can also measure the Reno stress of the accretion in the cavity, and that value can be as high as 10 to the negative 2. And the accretion rate can also be as high as 10 to the negative 10 to 10 to the negative 9 solar mass per year. And there's recent ExoArmor results showing that there is a strong correlation between the near-infrared access and the non-asymmetry index. The more asymmetric your disk is, the more near-infrared access it has. And there's also another strong correlation between the mass accretion rate and the asymmetric index. So our shadow scenario can naturally reproduce this because if you have a stronger shadow, you have a stronger accretion, and you have more material will be accreted into the inner disk and more near-infrared access. And we can also compare our simulation with observations. we post-process our simulation and compare it with this HD 142527, you can see both narrow shadows and their associated spirals. You may wonder why the shadow themselves leads to spirals, and it turns out to be something we have known of for many years, which is the planet-disk interaction. If you write out the Euler equation of motion, you can separate this pressure term into two. One is this asymmetric pressure, which is similar to previous study. And there's an additional term which is due to the shadow. Inside the shadow, you have lower pressure, you have lower temperature, and out of the shadow, you have higher temperature. And this term can be separated out into two terms again. And one of these terms, this divergence of temperature or divergence of sun speed square, acts as a planetary potential or a binary potential. So that's why the thermal perturbation themselves can launch shadows. And here I'm showing that the spirals produced by only 10% of temperature perturbation. And on the right-hand side, I'm showing Jupiter mass planets launched one-arm spiral. And you can see they are reaching similar magnitude. So the dynamical effect from shadow itself can be very strong. Not only we see spirals, we also see rings. If you run the simulation long enough, say 100 orbits, you can see concentric gaps and rings in the gas profile. And this is because of the coupling between the thermal forcing and the spirals. And then if you put dust into your simulation, such as the work in Alex Ziempra's work, you can reproduce these concentric gaps and rings in ARM observations. So let's switch gear and focus on these white shadows, which is due to the slightly misalignment between the inner and outer disk. And we also use a very similar simulation setup, but now just we change the inner disk geometry so that the shadow is not perpendicular to the outer disk, but just 30-degree misaligned with the outer disk. And if we start a simulation, you can see that the inner high-density region of the outer disk started to tilt it towards the shadow's direction. But there's no external torque here, so the angular momentum, total angular momentum should be conserved. And then if you look at the outer very low density region, you see that they are tilting in the other direction to conserve the total angular momentum. So that means this white shadow is producing a different mode. It can warp the disk, and but to conserve angular momentum, the inner and outer disks are warped in the very opposite direction. If you look at the slice of the simulation, the shadow is represented by this black, darker region. The inner high-density region is trying to align with the shadow, whereas the outer low-density region is trying to align the other direction. And not only we have simulations, we have a lot of data to test our model. For example, in this HD 143006, in ARM observation, you have an inner disk and you have an outer disk that has two rings. And the inner disk and outer disk are not in the same plane. Their mutual inclinations is around 30 degrees. And in the near-infrared scatter light, you can clearly see that one side of the disk is in the shadow and the other side is directly irradiated. And there is recent ARM observations on this object showing that one side of the disk have much higher temperature than the other side of the disk. On the leftmost panel, what you are seeing here is the temperature residue at the 12 CO emission surface, and their difference around 14 Kelvin, and the background temperature is around 35 Kelvin. So the temperature perturbation here is around 20%. And as I mentioned, 10% of temperature perturbation is equivalent to a Jupiter mass planet, and this would lead to very strong kinematic structure in the disk. And it is the case when you look at the non-Keplerian motion at 12 CO surface, you see this grand design spiral or some indication of spiral structure, and the magnitude of the velocity can be as high as 0.2 kilometer per second at 100 AU. So this is a very good testbed for our shadow disk interaction theory. So I'll just leave my summary slide here. Basically, the shadow can act as a driving force to launch spirals, and these spirals can lead to very strong accretion as high as 10 to the negative 2. And we can also explain the coexistence between the shadows and spirals in near-infrared scatter light images. And if the mutual inclination between the inner disk and the outer disk are not very large, the white shadow can induce warp and vertical motion. In reality, if you are not in this very small misalignment nor very perpendicular configuration, it is a combination of this spiral and warp modes acting together. And this would strongly shape the kinematics of protoplanetary disk. And we have a lot of observations right now to compare with our theory. So this is, we have a lot of hope on this direction. Thank you for all attention.
Hello, Arturo Ceballos, UNLV. Are these inner disks misalignments a permanent feature in the sense that is the shadow going to stay in that position forever, or is there also?
Yeah, that's a very good question. For some of these, we don't have we don't know. Like in the time span we observe them, they are staying there, but. In one of these disks, we do see, actually it's Paula's work on, sorry, it's in the first slides of my presentation. So in this disk, Paula do see that these two narrow shadow lanes are changing as a function of time, but they are not like sweeping all the 360 degree, but they just like jumping around. So depends on the precession rate of the inner disk and their mutual inclination. And it's also possible that the inner disk just does not precess and the shadow is staying there.
Hey, Shangjia, good talk, cool results. Adolfo Carvalho, Caltech. For the first case that you showed where you get this increase in the mass accretion rate, if the resulting accretion luminosity is an appreciable fraction of the initial stellar luminosity you had, then that should cause excess heating as well as you drive more accretion onto the star, right? How could that impact the result? Because you already have this differential temperature from the shadowing, but then you're potentially increasing the heating of the dust.
Yeah, we didn't consider the accretion heating here. Our mass are pretty low. And I would imagine, I didn't think about too much on the accretion heating, but if you are accreting a lot of material in the inner disk and that becomes optically thick, then you don't have that temperature variation anymore, and that will diminish your symmetry, and consequently you would have less accretion. In terms of accretion heating, that's a very, very good question, and I'll think about it and talk to you later.
Sounds great. Thank you.
Yes, Stefan Kraus, Exeter. You showed the case of HD 14306,
right,
which has in the southeast that bright lump in the scattered light. And so I was wondering whether you can explain that either with the spiral that you talked about, or maybe if the material that is in the shadow comes out of the shadow and then needs to readjust in the disk scale height somehow.
Yeah, I don't have a certain answer, but it's a real good question because this arc is just located at this transition region between the shadowed and unshadowed region. So it is hardly a coincidence. And I think later on when we put dust in the simulation, we would know better what the dust would behave in this case.
Okay, thank you.
Sure. Richard Nelson, Queen Mary, University of London. First of all, congratulations on very nice simulations. If you start off with just a smoothly warped disk, then the evolution there is towards realignment between all parts of the disk on some time scale. What you're showing is that if you start off with a modest initial misalignment, but with these shadows, that the actual system seems to be going the other way, that you're driving towards greater misalignment. Is that correct?
It's not, it's sort of, yeah, it's a good question. I think the picture is that the bulk of the density are trying to align with the inner disk. Mm-hmm. But in order to conserve the total angular momentum, there must be some very low density region that very outer disk warped in the other direction to conserve this original angular momentum at this preferable direction, z direction.
So where's that talk coming from? I understand the conservation of angular momentum argument, but I'm kind of interested as to what's pushing what.
Yeah, we also tried very hard. I think these torques are all internal torques, like due to, Do
they depend on the shadow in a very? If you switched off the illumination of the central star, would you see something different, or did you test that?
It's basically due to the temperature perturbation.
Right.
If you turn off the temperature perturbation, or if the cooling time is very long, you don't see this anymore. Yeah.
All right, thank you.
So, so you're saying if the disks are asymmetric, so the cosi like...
No, it's nothing to do with cosi. It's just if you take a continuous disk and warp it smoothly, instead of having a broken... This is like a broken disk, isn't it? You've got a discontinuous change in the inclination. If you instead imposed a simple, smooth warp on the disks, again, in the absence of shadows, to be honest with you, so just a disk which is not illuminated, it would evolve towards coplanarity on a reasonably rapid time scale. But here you're not seeing that.
Yeah, that's a good question. I think the difference is that in that case, it is the propagation of this initial warp, but there's no driving force. But here, it's sort of like a driving force, but it's not a force. So it's the shadow thermal forcing, and it's like internal force. Yeah. But it's more similar to the driving force, such as a planet.
I understand. Yeah. Okay, thank you very much.
Thank you.
Marcelo Barraza from MIT. Nice talk. My question is, if you need like the temperature deviation to go all the way to the midplane, and if you can use the shadow to constrain like the cooling properties of the disk, for example, because the shadows are like in the surface in 12CO and in scattered light, but not in the continuum that is in the midplane. So that's
it is in the midplane, and you are in the ExoAlma collaboration, and I read a paper from the Cuero, that dust continuum paper, that you do see that one side of the this disk is brighter than the other one. But it's just the way we present these dust continuum observations. We use this arc size hyperbolic stretch to highlight the like a lower brightness part, so that you see that these disks are more like very, very symmetric. But if you show them in a linear scale, in this disk, you do see that one side is brighter than the other side.
So how does that connect with the cooling properties, like to kind of?
Yeah, that's why I want to use the midplane tracer to see the temperature closer to the midplane. Just by showing that the disk is in the shadow is not enough to show that there's temperature variation, because the cooling time can be very long, and the shadow doesn't play any role there.
Thank you.
Okay, but yeah, we like to continue this discussion. Go, please.
Yuxin Li from UC Berkeley. You mentioned there is about 20% temperature change due to the shadow. I wonder how much is the variation in density and the pressure structure?
You mean the variation in pressure?
and also gas density.
Yeah, if you assume that the pressure is in equilibrium, then the pressure should not change in the phi direction, but they are not in equilibrium, so I don't know. Like, if you assume the pressure are the same in the phi direction, then at the higher density region, at the higher temperature region, you have lower density, and lower temperature region, you have higher density to compensate the temperature effect. But they are not in the equilibrium state, so
Yeah, I was wondering what's happening in the simulation, and yeah.
In the simulation, you at least from this kind of from this vertical shadow, we don't see much change in the density in the phi direction, even if you are in the shadow.
Okay.
So yes, that's what we need to look at it into the simulation. Yeah.
Okay, thank you.
Yusuf Farga from Concordia Observatory. I wonder about the origin of the misalignment. So it's often assumed that there is some perturber, companion, or planet which can induce torques on the inner disk and cause this misaligned orientation. And I wonder whether how can you disentangle the effect of this perturber from the temperature effect that you just modeled?
It's not. I don't think there's any conflicts here. As long as you have something, either a planet or something else, to warp the disk and cast shadows, you can have this temperature change, and then you have following things happening. I think it's really hard to know what's really causing this shadow. Like what caused the misalignment between the inner disk and outer disk? It can be planet on the inclined orbit. It might be some like late inflow that the outer disk intrinsically have different direction of rotation, angular momentum. Yeah, but I don't know. It's a really good question, but I'm not sure. As long as you have something like this, such a geometry, you would expect this, the dynamical effects here.
Okay, thank you.
Thank you.
Okay. Bennett Skinner, McMaster University. I'm wondering, because your argument here is that you have an inner disk, and then it brings a lot of the outer regions of the disk into alignment with it, and then the very outermost parts of the disk become misaligned to conserve angular momentum. So I'm wondering what mechanism causes this to stop? Why doesn't this just kind of keep propagating outwards, and the coplanar part of the disk keeps expanding out? When does it stop?
Oh, that's a really tough question. The answer is I don't know. We haven't tried to, because the simulation is very expensive. We haven't tried to extend our outer boundary, but we already extend our outer boundary to a very large distance. So yeah, honestly, I don't know, and maybe. After finishing this project, I have some more solid answer to you.
Thank you.
Okay, last question from Jack.
Is disk self-gravity completely negligible?
Here we don't consider self-gravity. And in that HD 143006 disk, at least the self-gravity is not very important. So yeah, we didn't consider.
Okay, thank you very much for that active discussion. Let's thank the speaker again. I'm sorry to reduce your break time, but come back at 4, right?